So that's what abelian means. It means that if you take any group elements x and y, then xy is the same as yx. That's what I've got to do. So how am I going to do that? Well, let's take x and y in G. But since I know that G is generated by A, each of x and y must be some power of A. So I'll call the powers a to the I and a to the j, where I and j are integers. So I know that I can write x and y like that because every element of G is a power of A. And then it's just a computation, and I'm going to use the index laws. So what's x times y? That's a to the I times a to the j. That's just writing down what x and y are. So there's a nice space down my right hand side where you hopefully are writing down reasons. So that's just from x is a to the I, y is a to the j. Now I'm going to use index laws. That's a to the I plus j. So that's index laws in the group G. Now, forget about the a for a moment and just look at what's happening in the exponent. I've got I plus j there, but I and j are just integers. So I'm just doing a computation in the integers up here. And we know that the integers is an abelian group. The binary operation of addition is commutative. So I can write that as j plus I. So that's a crucial step. It's using the fact that addition of integers is commutative. And then I just come out backwards. So I get a to the j, a to the I, using index laws again. And then I've got yx. So what I've done is prove that xy is yx. So we conclude that G is abelian. Okay, so that's proof, which involves the index laws, and of course we're using the definition of a cyclic group in there. We haven't got really much more than the definition of a cyclic group so far, so that's really all we can use. But we're using some general group theory stuff like the index laws. So every cyclic group is abelian. So if you've got a non-abelian group, you know straight away it's not cyclic. Okay? Now the question pops up then, since this was an implication in one direction, if G is cyclic then G is abelian, you could ask, well, is the converse true? In other words, if G is abelian, then does it have to be cyclic? And the answer is no. We've mentioned an example already of a group which is abelian but not cyclic. So this is important. The converse is false. So let's just give a counterexample. And as I said in the tutorial yesterday, or at least one of the tutorials, not often a nice little counterexample to fairly sort of straightforward results is the Klein group. And that's often denoted by the symbol V. And V is abelian but not cyclic. And just to remind you what the Klein group is, well, depends which model you're looking at. We introduced it as the direct product of Z2 with Z2, integers modulo 2 under addition, direct product with itself. You could just write down the group table. So if in Z2 cross Z2, I use the notation E for the identity, which is the ordered pair of identity elements, and then we've got three other elements. It doesn't really matter which way you do it. The other three ordered pairs, and then the Cayley table looks like this. So E is the identity element, and then the Klein group is immediately noticed by the fact that we've got a row of E's down the diagonal. In other words, the square of every element is the identity. By the way, I'm swapping from additive notation here to multiplicative notation here. I hope that doesn't confuse too much. So just focus on the group table if you prefer, but that's a model for the Klein group that we actually wrote down originally. So I can fill the rest of this group table in. From the cancellation laws, or equivalent the solution of linear equations in a group table for a finite group, every row and every column contains every group element exactly once. I'm not sure I've actually mentioned that in class before. It is mentioned in Fraley, sometimes called the Latin square property, because a Latin square is an array where each row and each column contains every object exactly once. So we can fill this in. So this must be C because it can't be B, so that must be B, and then we can fill the rest of it in a similar way. So once we've got that row of diagonal E's, there's only one way to fill this in, and this is the group table for the Klein group. So as you can see, it's abelian because it's symmetric with respect to reflection in the diagonal. So V is abelian. But it's not cyclic because there's no element that generates it. Because if you look at the various elements, the group generated by the identity is just the identity, and the group generated by A, well, it's going to have the identity, it's going to have A, it's going to have A squared, but A squared is the identity, so I get straight back to the identity after one multiplication by A. And similarly for B and C. So no matter which element I take in the Klein group, the subgroup generated by that element is never the whole thing. So I can't generate the Klein group from a single element. So that means the Klein group is not cyclic. So I'll just... okay? So the Klein group is a nice little example to have. It's an example, amongst lots of other things, of an abelian group that is not cyclic. Okay? And there are lots of other examples of abelian groups that are not cyclic, but this is actually the smallest one. Okay. We've now going to come up to this proof about subgroups, which is slightly harder, and to do that we need a little bit of number theory background. So this is why cyclic groups are a bit more difficult, because they do rely on a bit of number theory. Now I'm not sure if you did this in year 1 or even before, but the main thing we need is the division algorithm, which is something you probably did actually a very long time ago at school, where you're dividing one integer by another and you have a quotient and a remainder. So that's all we're using. We're doing there are lots of division algorithms depending in what situation you're working, but this is a division algorithm for the integers. So, as I say, it's just dividing one integer by another and getting a quotient and a remainder. So I'm just going to state it, I'm not going to prove it. So I'm going to take an integer n, and I'm going to take a positive integer m, and I'm going to divide n by m. I could actually take any non-zero integer for m, but just to keep things straightforward, I'll keep m positive, which is all I'm going to need. So I'm going to divide n by m, and then if I do that, I've got a quotient and a remainder, which I'll call Q and R. Q for quotient, R for remainder. So what do the quotient and remainder do? Well, n is equal to the quotient times m, the number that I'm dividing by, and then there's a remainder in general. And what's the remainder? Well, the remainder is possibly 0 if n is divisible by m. In general, it'll be some number between 0 and m minus 1. So it's strictly less than m. So that's the remainder. So Q is the quotient and R is the remainder. So that's a standard result from number theory, which you've seen before at some point. I'm not sure if you did it last year or not, but you might have seen it at school. You've certainly talked about quotients and remainders, I would have thought. So perhaps we do a quick example of that. So for instance, if I took n equals, say, 46 and m equals 7, then all I'm saying is I can write 46, I'm going to divide 46 by 7. So what I'm thinking of are multiples of 7, and the first multiple of 7 going to the left from 46. So there's 46. And I'm also thinking of multiples of 7. So there's a multiple of 7 here at 42. And in fact, that's the first one we hit going to the left. So the next one is somewhere here. Should be 49. So we just write 46 as 42 plus a remainder. And 42 is 6 times 7. And then there's a remainder of 4. So here's the quotient, Q, and here's the remainder, R. And 6 and 4 are the only numbers that work. Okay, so that's all we're saying. And you can also do this if the integer n is negative, and it's the same thing. You just track to the left until you hit the first multiple of the number you're dividing by. So perhaps we should do a negative example. Suppose I took n equals, say, let's do n equals minus 46. And let's take m equals 7 again. So if n equals minus 46, then tracking to the left, the first multiple of 7 we hit is minus 49. So we're going to write minus 46 equals minus 7 times 7 plus 3. So again, 7 is the number that we're dividing into minus 46. So the quotient this time is minus 7 and the remainder is 3. So minus 46, we track to the left, we get the first multiple of 7, which is minus 49, and we're writing minus 46 as minus 49 plus 3, which is minus 7 times 7 plus 3. Okay? So we can do this whether n is positive or negative, or indeed 0. The remainder, notice, is always between 0 and m minus 1. So if we're dividing by 7, the remainder is always between 0 and 6. So here it was 4, here it was 3. So that's the division algorithm, and we need that quite a lot from now on, because a lot of cyclic group theory just collapses down to some number theory. Perhaps collapses down isn't the right word, but we essentially use number theory to prove things about cyclic groups. So let me state a theorem, and then perhaps, since it's a bit of a slightly trickier result, we might have a little break before we do the proof. So here's the theorem, and in this theorem, the proof of this theorem, we're going to use the division algorithm. So let G be a cyclic group, let H be a subgroup of G. So we're now blending cyclic groups, which we've just started talking about, and subgroups, which we were talking about last week. So let G be a cyclic group, let H be a subgroup of G, then H is cyclic. So by taking subgroups of cyclic groups, we don't jump outside the class of cyclic groups, which is nice. We're not going to find any surprises in our cyclic groups, okay? All the subgroups are cyclic. Well, we'll do the proof after the break.